Taylor approximations. This is the theorem that we rely on, and we're going to do a little bit more of that, but this is, let's review the last example, which was a request to compute the square root of 4.01 approximately, not approximate, but rather without any tools other than what you might have like your hands, or possibly a calculator that is elementary as you know, like elementary school calculator. So so this is the request. Okay, so I put it in the quotation marks because it might come from, you can imagine that it comes from your boss, and then you supply the boss with the answer, and what exactly that it contains is up to you. Okay, the solution, as you can see, is very long, so you might fairly long. You might supply the whole solution, but or you can just supply the outline, and the outline is what is this picture? And the outline is just, well, the answer. So you might supply just the answer, which is this. This might be your reply. So in other words, you give the answer in the form of a single number, which is really, if you don't want to be provide an answer that is more sophisticated than that. That only requires our original theorem about Taylor approximations, linear approximations. In fact, if you again want to be more sophisticated, then you provide plus or minus idea. So giving the range of, not the range, but rather the accuracy. So that would be your accuracy that you guaranteed accuracy. Okay, so that number, or if you want to really be explicit about what you are saying, and so beyond any misinterpretation, then you supply that last line over here. So you're saying that number, that you are not saying where it is, what it is exactly, but you're saying in what interval it is absolutely guaranteed to contain in. Okay, so that's the interval. Okay, so once again, you can go on with the more sophisticated answer, and more sophisticated answer might be also you want to emphasize that you are supplying the linear approximation rather than anything anything more than that. Okay, so because it's linear approximation, and there was no requirement about the accuracy in the original request, that question here. Okay, so then you might include that part with your answer. I would also suggest, well, not certainly it's so hypothetical, but you might also add something like this. I could give more accuracy with more time, if more time is given. Okay, because the accuracy was not requested specifically. You were, based on your own judgment, picked the accuracy that was satisfactory to your mind. And the linear approximation is probably reasonable, because if somebody asks you what square root of 4.1 is, then the constant approximation is simply probably not what they're looking for, because everybody knows that you'd approximate it by 2. Right, so the next stage, your next level would be, or degree of approximation, would be a linear approximation, which is what you picked, and you gave the answer. But you also indicate that if you, I don't know, running for promotion or something, you could say that I could give more accuracy if more time is given. However, beyond that, you might be requested. The request might be more specific in that way, and so you might be asked for specific accuracy to be provided. Okay, so let's look at that example like that. So example might be give e negative 0.01 within 6 decimals. So that answer might the answer to this might contain a single number, but there is actually more work to be done than the previous one, because the accuracy has been requested. So then you have to satisfy it, and so you have to go all the way back to the to this theorem of approximation theorem. Okay, this theorem, and the problem is that you do not get to pick the approximation, so you cannot pick linear or you cannot pick quadratic. Which one is it? You don't know until you carry out this analysis. You have to carry out this analysis to find out what your n is going to be. Okay, and then n will give you the accuracy that is requested. So let me carry out this solution. So what we are looking at is, fortunately the function is simpler, so we don't have to do too much work. So we are looking at f of x equal to e to the x with all the derivatives, f prime of x and so on, they are all equal to e to the x. Okay, a is equal to 0. Okay, so that why? Because f of 0 is known to be 1. Okay, so we are looking, it lists the value of the derivative of the function, and of all its derivative needs to be known in order to carry out such an approximation, and indeed all the derivatives of all degrees will give you the same number. So which means that we already have all the coefficients of the Taylor approximation. Okay, so Taylor approximation then, as we know, will be at zero, fortunately, will be summation k from 0 to n, 1 over k factorial, xk. Okay, so that's my nth degree Taylor polynomial at x equal 0. Okay. So it's a polynomial, and its degree is n, and the better n is, the better approximation is. So once again, let me take you to that picture of the approximation of the exponential function approximation. This is the one. Okay, so exponential function around 0, linear, quadratic, that's the line in the middle, row in the middle, we have constant, linear, quadratic, and cubic approximations. The accuracy of approximation is getting better, as you can see, but which one is it? We don't know, because from the picture you cannot tell how accurate these are. Okay, so we have to look at the actual numbers. Fortunately, we can use simply the error bound. The error bound is x is equal to 0. Well, rather, let me put it this way. Let me write the inequality first. So Tn x minus fx, okay, less than or equal to k sub n, x minus 0 n plus first power over n plus 1 factorial. Okay, so that's the error bound formula. Okay, so the Taylor polynomial is specified, n is not specified yet, f is what we're trying to find, kn is still to be found. Well, actually it's n plus 1 over here, and it is the, remember what it is the estimate right here in green, the estimate of the n plus first derivative of the function. Fortunately, it's the same function. So we can easily now estimate. So we need, in order to continue with this, we need kn plus 1, okay, which is, where does it come from? It is fn plus first derivative of x less than or equal to kn plus 1. Okay, the derivative is, fortunately, is simply our derivative exponential function, so it will be e to the x less than or equal to kn plus 1. and the issue that we faced yesterday was looking at the shape of the graph of the function in order to come up with an estimate. Okay, so it is you cannot have an estimate like this for the whole domain of the function because it goes to infinity anyway. But you can think of if you look at the picture, you can tell. So once again, this is my exponential function. So we're looking at 0, which is this. So that's my a. Remember, we're supposed to look at is the interval from. Let me do it this way. So this is my x, which is negative 0.01. Okay. So in other words, we have to concentrate on this interval. This is the interval. On this interval. So when x lies between these two numbers, okay, we have to have an equality, this inequality, and we need to pick a number. It doesn't matter what the index is. We just need a number. Okay, so we have an idea from last time. So what do you think the estimate should be? It should be 1, right? Because why? Because we are only looking at this piece of the graph, and it lies between and it crosses the x-axis at 1. It is the exponential function base e. It crosses the graph at 1, and everything lies below this. Okay, so this will be my k. The graph of my function lies below it. Okay, so that is not only an estimate; it is the best estimate because we cannot make it any smaller. Okay, so k, choosing based on this. Once again, we just like yesterday, we observe that the function is increasing. So e to the x is increasing. That is why everything will not go above 1, and we pick k n plus 1 equal to 1. Okay, then my estimate becomes my error estimate this time. My error estimate this time becomes what? It becomes what is it? Tnx minus negative 0.01. Okay, that's what we're looking at. Less than or equal to 1 times x n plus 1 over n plus 1 factorial. Okay, so that's what my error estimate gives me. So at this point, everything is specified. We assume that our Taylor polynomial is given. It is a polynomial, so we can compute it any time we want. So we're not worried about that. And on the right-hand side, everything is determined too. The only thing remains undetermined is n, and it is in fact the one that we have to figure out what it is. So in other words, what is the problem now? How we put it? Find n such that Tn of it's not of x as much as 0.01, negative 0.01 over here, such that T negative 0.01 minus E negative 0.01 is less than what is it? 6 decimals. So 10 negative 6. Okay, so these are the two things that we have to look at, number 1 and number 2. So number 1 is what we've got, number 2 is what we have to find, and so we have to use the first inequality in order to figure out what n should be in order to turn that inequality into the second inequality. Okay? So in other words, how do we guarantee? We need to guarantee this. We need to guarantee this. And how do we guarantee this? How do we guarantee this? This is also 0.01, I'm afraid. Let me put it side by side, maybe make it clearer. So side by side, like this. Okay, what happened? Okay, absolute value. Okay, so so as you can see, the left-hand side is the same. And it depends on n, and once again this is given, or this is what we have, and this is what we need. We need to guarantee the second inequality based on the first inequality by our choice of n. So how do you guarantee it? What is the relation that we should establish between these two?
So equal to each other?
Oh, not equal necessarily. I mean, equal, yes, but anyway, yes. If they are equal, then we're good. We cannot guarantee that it will be equal, considering that n is an integer. So we cannot guarantee that, but in essence, that's what we want. We probably will have to choose an n larger than that we would find from the equation. So since I was going to go for an inequality here, but we could go with equality as well. So solve the equation. Once again, this is the equation that I'm talking about. These two are equal to each other. So negative 0.01 absolute value divided by n plus 1 factorial is equal to 10 negative 6. This is just an equation, so we solve it for n. Let me rewrite it. I have what? I have 0.01 times 10 to the 6th, supposed to be equal to n plus 1 factorial. So for n is what we are after here. Okay, so keep working. What's next? I'm afraid that's not right. I missed something while I was doing copying. I missed this part. Sorry about that. N plus 1 is the power here. So this is n plus 1 over here. We have n plus 1 here. Okay, so let's simplify. We'll have what? N plus 1 over here. Okay, so how do I simplify the left-hand side? I need to solve for n, so I need to. How do you take a natural? How do you take a natural log of the factorial? Well, we will figure it out by experiment, but I want to simplify the left-hand side first, and then it might be clear what we're talking about. 0.01 is a power of 10, right? So what is it? 0.01 is 10 to what power? Minus 2, so I have 10 minus 2, n plus 1 times 10 to the 6th is equal to n plus 1 factorial. And then I have, now what do I multiply the powers, right? So I'll have 10 negative 2n plus minus 2 plus 6 equal to n plus 1 factorial. Or I have 10, 4 minus 2n, n plus 1 factorial. Let me check my computations. Okay, so 0.01, I have negative 0.01 nth power. Yeah, okay, n plus first power divided by n plus 1 factorial. I have an equality over there to solve. N plus 1, n plus 1, n plus 1 to the numerator, 10 to the 6th. I have negative 10, negative 2, negative 2n minus 2 plus 6, 4 minus 2n. I have, why do I have difference here? Okay, yeah, I have a mistake there. So this seems to be okay, right? Does it seem okay? Okay, so from this we need to figure out what n is. We could how do we do it? We could plot it. We could experiment with n's. Something that we know about. Is this right? Why does it feels wrong? Negative 6. Minus 7. So it does have to be equal. The inequality is will be supplied, but if we try to solve it, that's why the logarithm is really of no help here because of the n factorial. But what I'm worried about is when the left-hand side and the right-hand side goes to infinity, the left-hand side actually goes to 0 as n increases. So certainly there will be an n that will give us the correct answer. Okay. So let's combine them together again, I think. Okay, here it is. Here, the way I want to do it: n plus 1 factorial times 10 to 2n. Okay, is equal to 10 to the 4th. Okay, so I move stuff around. I want to have n on one side. So now you can see that 10 to the 4th is a fairly large number. So we would have to make n fairly a large number in order to fulfill this requirement. Okay, so and then any number n larger than this would be satisfactory. Okay, did you see what I did? I pulled the 10 negative 2 to the right hand side. That's all. So then it becomes positive, right? So it's division by 10 to the n, and then it becomes multiplication by 10 to the n. Okay, so all right. So it remains just to find the appropriate number. You could try to go through experiment. So let's just do it since we're doing everything by hand. Let's just run through this. So n here and over here I'll have that expression over here. N plus 1 factorial 10 to 2n. Okay, n is equal to 1. What do I have? 2 factorial times 10 squared, which is 200. What's the conclusion? Not good enough. No, it's not equal. We're not really after equal. First of all, it's probably never be gonna equal because once again, as an integer, so you are not likely to end up at exact value. Because we are skipping values, so two equations, when you solve equations for integers, you're bound to, most of the time, not to find any solutions because the exact values never equal to each other. When you're skipping, you have to imagine you have two curves and you're looking for the intersection, except this time these are not curves, but they are made of dots, separated by gaps. Okay, so which means that you might pass through through well, in fact, if you think about it, this is what we're trying to do. Suppose this is my n over here, and I have my graph, which might look like this, right? It grows with n, but what I'm trying to find is the intersection with this, y equals to 10 to the fourth. And we're not going to hit it exactly. We'll skip it. Okay, so what we're after is, in fact, this. This is the one that we're after. The one that the first one as we passed 10 to the fourth. Okay, so let's keep going. So 2, I have 3 factorial 10 to the third, which is 6,000. Right? Is it 6,000? So this is no, and this one is still no. Right? So we're still below that line. So this is, we tried 1, no. We tried 2, no. Let's take 3. It will be 4 factorial times 10 to the fourth, and in other words, it's 12,000. No, 120,000. So it's a yes. So we have passed that value. So in fact, this is, if we are trying to, if I want to have this semi-distant illustration here, then this is my n, this is my 2, and this is my 1, and this is my 3. So a sequence as a sequence of values of on the y-axis. Okay, so it grows fast, as you can see, indeed, by 10 at every time at least. And as soon as we hit, as soon as we pass 10,000, we're done. So then n equals 3 is our answer. I have n equals 7 here. Okay, so n is equal to, hold on a second, yeah, n is equal to 3. N is equal to 3, so, okay, n is equal to 3, our answer, which means that we're talking about cubic approximation. And now we can supply, all it takes is just to take our Taylor polynomial over here and plug in n equals 3. That's all. So what we're talking about, T3 of x is summation k from 0 to 3, 1 over k factorial x k. Okay, so specifically our interest is in T3 negative 0.01, so it will be, let me write it out. The first one will be simply 1. The second term is k, so that's k equals 0. K equals 1, I have x, which means that negative 0.01. Negative 0.01 is second. The next one is negative 0.01 squared multiplied by what? What's the coefficient? The second Taylor coefficient, what is it? Just plug in k equals 2. So it's 1 over 2 factorial, simply 1/2. And one more, k equals 3. We have negative 0.01 cubed, and the coefficient is 1/6. Okay, so all remains is just to take a calculator, an elementary calculator, and run out these numbers. This is all can be done by hand because these are just powers of 10. So you take a cubed square of these numbers, divide by 2, divide by 6, add them together, you have the answer. So you can do it by hand. I'm not going to do it, but that number you would supply as the single answer that is required because you have fulfilled the accuracy. And then you have that's all you need to say. Okay, so it turns out that the cubic degree polynomial is good enough. Third degree polynomial, cubic polynomial, third degree Taylor polynomial gives us the answer. So this is the answer. Okay. So any questions about this? So we actually found, what did we find? Remember, it was E negative 0.01, so we didn't even know what E is. I mean, E itself needs to be approximated. If you want to approximate E, you pretty much can do the same story here. So we found a certain power of E without knowing what E is. So similarly, you can, if you need to approximate E, you need to approximate pi, any kind of a transcendental number. You can also just go to a function that provides you with that and carry out a Taylor approximation. So if I want to actually approximate E, what do I do? To approximate E, actually E, to approximate E, what do I do? What is the function first? What's the function? Well, it is e to the x, right? And at what value? No, what I meant is you would approximate. Well, maybe I'm wrong here. Well, you actually have to take the value at 0, because if you don't know what E is at this point, the only value for the exponential function that you do know is the same value 0. Okay, so which means that you actually have to be fairly far away. You are looking at the polynomial, Taylor polynomial centered at 0, yet you are interested in e to the 1. So which means that the step of that that has been small. This one, the previous example, the step away from the center was 0.01, and now this step will be actually the value of 1. Okay, so which means that to achieve any kind of accuracy, you would have to have a very high degree, very high value of n. So that certainly requires extra work, even though the other than that, the work is exactly the same. So once again, I'm trying to find out what e to the 1 is based on nothing but the value of the function at 0. So this analysis goes through exactly the same way. So that's my function. This is my Taylor polynomial. The degree of the Taylor polynomial is the same, is n, so unspecified. The inequality is the same. The estimate is the same, so this still works out because no, it's actually it doesn't work out because we will be looking at the integral to the right of 0, which means that what kn plus 1 could be larger than e. So as long as you know that, say, e is less than 3, right? So you can use kn plus 1 equal to 3. Okay. And then what does it change? Not a lot. The rest is once again the same. So the only thing that changes is I would have like a 3 here somewhere. Okay, so which means that it doesn't really look that bad, does it? So in fact, it appears that you're still gonna need no more than a cubic Taylor polynomial in order to have the same 6 decimal accuracy, it appears. Well, anyway, so that's how we approximate things. We can approximate with any accuracy we want, and that is really what what we're gonna start talking about. Any degree of accuracy. This is especially the previous example was degree of accuracy was just given to us. We started with linear approximation, then we found its accuracy. Okay, this one we're stepping in the right direction. Any accuracy required from us can be provided. Okay, and that's what we have. You can imagine how if the next day your boss says, well, I was asking for 6 decimal yesterday, now I want 10. What's going to happen? Not much. You just repeat your process. That last inequality will be slightly harder to fulfill, right? So what's going to happen is over here you're going to be changing, right? So you're going to hit rather than what is it? 2 to the n. What is it? It would be 6 here. No, wait a minute. So this 4 is 6 minus 2, and we'll have 8. So if you need 10 decimals, if your boss needs 10 decimals tomorrow, all you have to do is just replace that 4 with 8, and you see how that you might have to do more steps here, but you know you can do it. You can do it because, well, through that experimentation, at some point you'll hit the number above what is that number, 10 to the 8th. Okay, so so at this point, we sort of set this aside and look at it in a more theoretical way, and just ask ourselves, where is the end of this process? And we realize that we're looking at sequences. We made that circle to that topic that we had mid-semester, sequences and their convergence, and we have a sequence. What is this if not a sequence? It just happens to be a sequence of numbers. If x is fixed, then it is nothing but a sequence of numbers. So we have a sequence of numbers for each x. What does it mean? It doesn't mean a lot. It simply means that we have, rather than having a sequence of numbers, we have a sequence of functions. Okay, so that's what now we're going to be concerned with, sequences of functions, which is really not a big deal. You can have sequence of numbers, you can have sequence of functions. For example, fn of x is equal to, I don't know, x to the n. A bunch of power functions, and they just grow. For each x, it is still just a sequence of numbers, but taken together, it is a sequence of functions. But the question will be the same, and that is there a limit? So it's convergence. So does it converge? And what does it mean? Well, turns out we already have the answer to that. If we just go back to the error bound. Let me copy this so I can discuss this. What happened? Okay, so this is my error bound theorem. The starting point is a function. This. So okay, let's set that aside. But the interesting fact is that every function is supplied with its Taylor polynomials, and together they form a sequence of functions. Okay. So the way they might look like is, once again, look at it. This is a sequence of functions. If you look at all the red curves, it is a sequence of functions. No matter where it comes from, it is nothing but a sequence of functions. If you certainly understand that this keeps going on forever. We were talking about infinite sequences of functions. Okay, so and then let's look at the inequality one more time. Not here. This inequality. Okay, and let's ask ourselves what happens if we fix a value of x. So fix x. What does it mean to fix x? It means that I will not think of these functions, t and x, as functions, but rather numbers, right? If the input is fixed, then it is a number, one single number. The output is also a single number. So then t and x is a numerical sequence. It's not a sequence of functions anymore. It is a numerical sequence. Okay, to begin with, and then f of x is also a number. Okay, so that's the left-hand side, takes care of it. So this is nothing but a number on the left. And then what is on the right? Once again, we have a sequence of numbers. Okay, so these are numbers. And it is a sequence of numbers. And now let's ask ourselves what kind of sequence that is, the one on the right. Okay, so well, let me make my life simpler here. Let me make this specific. So I'll say f of x is equal to e to the x. T and x is, we have already that Taylor polynomial is given to us. So a is equal to 0. It is 1 over k factorial x k, k from 0 to n. Okay, then my error estimate also we just discussed. So ex minus t and x is less than or equal to, k was 1, remember? So it will be x n plus 1 over n plus 1 factorial. Okay, and then let's just look at this number, which is some kind of simple sequence. So I think x is fixed, so once again it's just a number. Let's say it's not 0, but suppose n goes to infinity. What is happening to the sequence? So we divide by n plus 1 factorial while n is growing. N plus 1 factorial, what's happening to the factorial as n grows? Where does it go? To infinity. Okay, the reciprocal goes where? So the numerator, this is the numerator, this x, n plus 1, yeah, we did discuss the issue of the comparison of the, and this is, I guess, what the confusion is about. We didn't really discuss that extensively. We are comparing here two functions, and one in the numerator and the other one in the denominator. The one in the numerator is the exponential function, and in the one in the denominator is the factorial. Okay, the question then becomes, which one is stronger? The factorial. So factorial will overwhelm the exponential function and it will bring the whole thing to zero. Okay, so that's what I'm saying here. It certainly requires some justification, and I hope we may have discussed it. I remember that I did mention it, but we didn't really discuss it. But you can probably how do you? It's not entirely obvious how you demonstrate that, so I'll just put it aside, and let's suppose we know that for a fact that the factorial is not only bigger than the exponential function, but as a matter of fact it will overwhelm it just like exponential function overwhelms every other function that we know, for example all the power functions. So the exponential function is stronger than any function of any power, but the factorial is even stronger. Okay, and so it brings the whole thing to zero, which means, what does it mean? It means that we have this convergence of a sequence, this t and x converges to e to the x as n goes to infinity. Okay, so that's what we're saying. and that is the idea that we're gonna now explore. So this is the definition: a sequence of functions Fn converges to f, another function, pointwise if Fn x minus fx converges to 0 for each x in the domain of f. Okay, so convergence of sequences as opposed to convergence of numbers, but it is explained in terms of convergence of sequences because once again, this is a sequence of numbers. So what we discussed previously applies. This is a sequence of numbers. Okay, so so that the idea is quite profound. So we need to discuss it before we start applying it. Our main interest is still Taylor polynomials, but there is a way to look at it broader, and it is worthwhile. Let me start with a picture. So once again, for a moment, we'll forget about the here it is about the Taylor polynomials, and just look at this picture. Where we have a sequence. You can see a sequence. Okay. How the swing becomes smaller and smaller and smaller, and you can ask what is the limit of the sequence of functions. What is it? What? Well, one way to do it, if you are still unsure, just look at it once again, fix x. So this is what I'm doing here. Like this. Concentrate on the piece of the graph. Okay, so ignore the rest of them and look at these values separately. Point, number, 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 and just see where they go. And they go right here. And then you carry out the same plan for every point on the graph, and then you'll see where they are, and they will give you this. They give you the 0. So the function altogether, taking pointwise limits of these functions, will give you 0 at the end. The whole 0 function, not one number. It is a whole function. Okay. So I'm out of time. So there will be homework later today.